Welcome back. So I've said that there are only a couple of situations where I can really analytically solve for eigenstates for wave functions in one dimension. Well, today we're going to be talking about the sort of ultimate analytic solution to eigenstates in one dimension of a Hamiltonian, because it's the Hamiltonian that we go to when we need to approximate just about any system. And this should remind you of what we did in Physics 245 and maybe what you're doing in classical. If I have some potential that has some stable point of equilibrium, I'm always going to think about looking at that potential near that equilibrium as an important place to look for physics, right? That is, near equilibrium physics describes most of the phenomena that we see and that we study. And so it's important for us to zoom in on the potential near a minimum so that we can understand what happens when I'm studying near equilibrium physics. And of course, if I look to that, right, I know there could be some offset, right, in the potential. And of course, I'm Taylor expanding a general potential about its minimum. Oftentimes, the constant term doesn't matter to us because there are no forces associated with that constant term, and therefore it doesn't tend to enter into the dynamics. The next term of my Taylor expansion also vanishes because I'm at a minimum, right? And therefore, that's defined to be a critical point where the derivative of the potential is zero. And so I'm left with the most important term in the Taylor series being the quadratic term. Okay, and if I'm at a minimum, that means also that the second derivative of the function with respect to x is positive, right? So that way it's a minimum, right? It's concave up. And if I plug that back into f equals ma, I can get a relationship between sort of the natural oscillating frequency from a classical sense about that minimum and m and k, the value of the second derivative of the function. Anyway, all of this is to say that a good approximation to a potential is going to be given by a quadratic function as long as I'm studying the dynamics near equilibrium. And therefore, thinking about what quantum mechanics might exist in this potential minimum is going to be really exciting because in general it's going to be applicable to almost any real field or real potential that I can set up, right? If I'm going to be, say, wanting to trap something quantum mechanically, right, the potential that defines that trap is going to have some regime where it really does look like it looks like a quadratic, and therefore we're going to call that the harmonic oscillator, because it corresponds classically to a harmonic oscillator. But it's the potential that defines the quadratic minimum. And so if I plug that into my Hamiltonian, I get that the Hamiltonian actually has kind of a neat form, right? It's the p squared over 2m from the kinetic energy plus the something proportional to x squared from the potential energy. And already this problem is setting itself up to be a beautiful theoretical problem because my Hamiltonian is sort of made of two parts, one of which goes as p squared and one of which goes as x squared. And so we're already building this symmetry about contributions to the total energy from both the momentum squared and the position squared, right? And that, of course, is what leads us to all of those beautiful things that we saw in oscillations and waves. But if I take this potential and I want to study it the way that we've been doing, I want to plug it into the eigenvalue equation for the Hamiltonian and see if I can solve for some bound states of this system. So using Griffith's rule, I can turn the eigenvalue problem into a differential equation, right? A second order differential equation that tells me the relationship between all of the energies and the eigenvalue of the energies, which I'm going to call E. Right? And like with all of the systems we've been studying up to this point, the question is, are there a set of wave functions such that I can solve this problem? And that is, are there wave functions such that the left-hand side of this gives me just a constant energy times the wave function itself? Do they satisfy this eigenvalue problem? And there are really two ways of doing this. Way number one is to solve this using boundary conditions, and that probably needs quotations around it or something because my boundaries here are really going to be quite far away and I'm going to have to use some pretty fun tricks of differential equations in order to do the problem the way that that I want to, right? To do the problem by explicitly solving the second order differential equation using the tools that I have. And then there's this alternate way, once maybe it's a good thing to do second, but to seek a better formalism. Like, are there some mathematical tricks I can play that might save me some of the headache of solving this problem using the boundary conditions? Well, today, because this is our first foray into the harmonic oscillator, we're going to stick to the old-fashioned way, okay? Maybe this will just convince you never to do the old-fashioned way, but we're going to stick to the old-fashioned way because I want to show you how we can literally solve this problem using good old-fashioned tools of differential equations and using the intuition that we've developed for how boundary conditions can give us quantization conditions and how boundary conditions can give us they can help us to understand why I only have certain allowed solutions to an equation. So I'm also going to caveat this entire thing by saying that the method that I'm going to use here is not widely applicable, right? So one of the things that we've learned in our journey through physics about differential equations is that oftentimes we need a new method of solving differential equations for every problem that I have. Luckily, if I have a differential equation and I find a solution, I know that that's a solution. It doesn't matter how I found it, right? And so bear in mind today that I'm not going to expect you to know how we did this, right? I'm not going to expect this to be something that, I'd sit down on a quiz with some new, some problem like this and say, hey, find out what the right method of solving this differential equation is. This is going to be a procedure that's interesting to learn, and it's going to hopefully be fun for you to watch me go through it. But it's not something that I would have imagined you came up with out of nowhere. Okay. So the first thing I'm going to do, and this is probably going to be your favorite step of this process, is I'm going to take my physics equation that comes from the eigenvalue equation for the wave function, and I'm just going to solve it for the second derivative with respect to psi. This sort of makes it feel a little mathier. A lot of times when we study differential equations, the first term is always going to be the highest derivative, and it's going to be alone, and then I can move things to the other part of the equation. I should say, in the old days, in the before Mathematica times, what we probably would have done is we probably would have looked for solutions to this equation in some big table of integrals. We won't quite do that yet. I'll walk you through some of the algebraic steps. So the first thing I want to do is I want to think about the boundaries, right? So can I use information about what's happening in the boundaries of this problem to help inform what kind of solutions we're going to have? And so for that, I'm going to say, well, what happens if I go far away from the middle, right? Because my boundaries here aren't fixed, right? They're really at infinity. I have my parabolic potential, but there's nothing stopping me other than very high potential energies from going all the way to x equals infinity. So as I go there, though, one of these terms is really not going to be as important. After all, the last term here has an x squared in it, right? So as I go towards infinity, I get an infinity squared, and that's going to be more important than any finite term to which I'm comparing. And so what I'm left with is something that says, well, the second derivative of psi is sort of related to psi. It's a kind of fun place to look for some sort of exponential, and because the second derivative is related to x squared times psi, the kind of exponential that we're going to look for is something that looks kind of Gaussian-y. That is, we're going to try to say that the potential at far distances is going to be governed by a Gaussian-looking function, which is e to the minus m omega over 2h bar times x squared, okay? And then I'm going to have some other function that I'm going to find that's going to sort of be important near the middle at smaller values of x. But it's not going to, that function isn't going to be big near the boundaries. This Gaussian is going to really tamp down any other functions to make sure that the Gaussian is in control at large values of the field. Now, many of you are probably saying, why do you know that that's true? Or how do you know that that's going to be there? Right now, it's just a guess, right? And that's what differential equations tells us we can do. If I make a guess and it solves the problem, then it's right? right? And that's one of the fun things about differential equations. Should I have known this before going into the problem? Well, probably not. You can imagine that at some point somebody, spent a half of their career plugging in different functions and different boundary conditions and trying to get what this thing should look like. And so I'm informed by that, right? And I'm guessing that this is going to be what the asymptotic behavior looks like as x gets big, or if x goes to positive or negative infinity. But it is clairvoyant, right? I mean, it comes with the history of knowing that this is probably going to be a useful thing to do, okay? And it's not necessarily something that we would have known or that we would have come up with on our own. But it's also it's a fairly common technique. It's one that we'll use one more time towards the end of the semester, where I take psi, which is sort of totally unknown, and I break it up into the product of something that I totally don't know and something that has a behavior that I like. And in order to use this, though, I have to take psi and I have to take a bunch of derivatives of it so that I can plug it back into my differential equation and now get a differential equation for u, right? So that's still that piece that I don't know. I'm going to hopefully come up with a differential equation that describes it, so that I can solve that, right, instead of my original differential equation. And looking at the steps of coming up with first the first derivative of psi and then the second derivative of psi, sorry for missing the 2 there, it's horrendous, right? Like if you weren't a mathematician or a physicist, you'd be like, you're going out of your mind trying to come up with some analytic form for this. Why not just use a numerical simulation? Okay, that's a different lecture. But in order to plug it into the equation that I have, I need to know, well, what is psi, what is the first derivative of psi with respect to x, and then what is the second derivative. And I can do a little bit of simplification, right? So the second derivative of psi with respect to x eventually gets written as 3 different terms. There's a u double prime, a u prime, and a u. And what I'm doing is I'm changing the problem from a differential equation for psi to a differential equation for u, right? So now I can plug these back in, right? So I'm trying to include now everything on a single slide. The blue equation was my original equation, this one here, right? That's just the equation I get from the eigenvalue equation. The red equation is the substitution that I'm going to make for psi, and then the green thing on top is what I derived on the previous slide, which tells me how are the second derivatives of psi related to all of the derivatives of u. So I plug all of that in, and I end up with this beautiful red equation down here at the bottom, which, again, any sane person would be like, what are you doing? That looks so much worse, right? I mean, I had 3 terms. I now have 5 terms or something. Oh, yeah, it does look worse, but luckily, it's worse in sort of a simpler way. I can pull everything together, and now I have a differential equation for u. Okay, and it's still a second order differential equation. I sort of don't have any idea of what's going on at the boundaries anymore because the boundaries are taken care of with the parameterization of psi. Well, how do I solve something like this? It's actually, I don't know. I don't know how you would come up with the method, but the method that we're going to do to solve something like this is to try to guess that u is perhaps a polynomial. Okay, why could u be a polynomial? Well, we don't have to worry about boundary conditions. That's taken care of with that Gaussian that I'm eventually going to multiply by u. But it's possible, it's sort of polynomial-ish, right? So maybe there are polynomial solutions. I don't know what they're going to look like, but if I say u now is going to be some sum over alphas times x to the n, right? So this is saying that u could be any polynomial from a constant to any possible powers of n. It's something that could perhaps be a way to solve for u. Again, in order to solve the differential equation, I need to take u prime, and u double prime, where note I'm starting the sum 1 term later for each of the subsequent things, because it doesn't really make sense to plug in n equals 0 to the bottom equation. I guess it will be 0 just because of the way it's written. But those terms vanish, right? When I take the derivative, the 0th term doesn't exist anymore, and when I take the second derivative, the 0th term and the first term both don't exist. Anyway, I have expressions now on how to relate u double prime and u prime and u to this power law substitution. Okay, and that's probably what it's called, right? Polynomial substitution power law. Anyway, it doesn't matter. I'm going to plug this in, and now again I've changed the problem, right? First it was a second order differential equation for psi, then it was a second order differential equation for u, and now it's going to be, can I figure out what these alphas are? Okay. I'm going to plug in all of these things. I get all these different sums. It so happened that in the second term, there's an extra x. And so the second term has an x to the n for every term. And the last term has an x to the n for every term. And so that allows me to take these two terms, which before I couldn't combine, and combine them into just one term, right? Where that one term is collected by powers of x to the n. Now this first sum has an x to the n minus 2, right? I can't automatically combine that with my other terms unless I re-index it, right? And again, this is why before I was starting at n equals 2, if I redefine n so that the old n equals 2 is the new n equals 0, that just makes n go to n minus 2, or sorry, that makes n go to n plus 2. And now I'll have an x to the n, but all of my old n's change to an n plus 2. And so I have a second term which relates the alpha to the n plus 2 to x to the n. Okay? And so now I have a relationship that inside these hard brackets is something that gets multiplied by every x to the n, which is eventually, going to have to be equal to 0 to solve my differential equation. And now this looks a little bit crappy, but it's actually not so bad, right? Because in order for this sum to vanish, and my sum, remember, is now written as something times x to the n, in order for that really to vanish, every single term in that sum is going to have to vanish, right? If one of those terms doesn't vanish, then I'm going to have a power of x to the n that isn't going to be 0 anywhere, right? And so every single one of these terms is going to have to vanish in order for that whole sum to vanish. And so that whole thing in brackets has to vanish, and what that does is it allows me to come up with a recursive relationship that tells me I can find out what alpha of n minus 2 is. That is, what's the coefficient in the power law in the polynomial for the n plus 2th term related to the nth term. Okay? And again, remember what this means is that when I'm reconstructing the function u, I need to know what all of those alphas of n's are. I multiply them by x to the n. I sum over all of the n's, and that gives me what the function u is. Then I plug that into my definition for psi, and that gives me what the wave function looks like. So, in short, this is how I could find all of those different coefficients to figure out what u is. And that's really cool, right? Because I've actually solved the problem at this point. Some of you are like, you've solved the problem at this point? I've actually solved the problem at this point because I could reconstruct the u's, and once I reconstruct the u's, I can reconstruct the psi's. Okay? I can get the wave functions out of this. But what's more interesting is the fact that we have to remember the whole point of this was to find out, are there only specific functions allowed? Are there only specific wave functions? And it turns out, hidden in this slide, is the answer to that question, which is yes, right? In the sense that if I think about the different solutions to this being different polynomial orders, right, then I can insist that for a particular solution, you only take terms up to x to a certain power. That is, if I come back down to this bottom expression here, I say, well, maybe there's a solution for which alpha sub 0 is the only term that exists. Or is there a solution where I have the alpha sub 0 and the alpha sub 1? Or the alpha sub 0, the alpha sub 1, the alpha sub 2, right? Can I truncate this at a given polynomial? And the answer is yes. And that's exactly what this recursive explanation says. That if I set alpha sub n plus 2 equal to 0, then I can generate all of the alphas up to that point. Okay, and that's what's going to allow me to truncate this expression. And so if I can do that, if this is finite, that means that the numerator on this expression is 0 given some n, right? So I start with some alpha sub n, it's not going to be 0, but then the alpha sub n plus 2 is going to be 0, so the numerator has to be 0, and if the numerator has to be 0, then I've actually quantized the energy. And the simplest of all expressions comes out of this after all of that tedious algebra and calculus. This thing is equal to 0 when E is equal to h bar omega times n plus a half. All right? And what this means is that if I allow my wave function to have one more term in that polynomial, if I allow u to have one more term, I've gone to a different energy state where that energy has increased by 1 h bar omega, right? The 0 one, the one where I only allow for there to be a constant term, that has energy h bar omega over 2. If I have 2 terms in the polynomial, I have 3/2 h bar omega. If I have 3 terms, I have, I've increased by another h bar omega. And so I have evenly spaced energies, one energy level corresponding to every time I add another polynomial to u, which gives me a new wave function. Okay? And that was a really long way of getting to this expression. Now, if I want to reconstruct what those polynomials are, luckily there actually is a name for them, right? If I want to reconstruct my wave functions by taking u and multiplying it by that Gaussian, well, those u's happen to be a family of polynomials that are known as the Hermet polynomials. And there's a normalization factor that comes out in front. And I'm giving you this just because it's sort of an interesting thing. It's an interesting thing to know that I can have these Hermet polynomials here, which allow me to evaluate the actual wave functions. And so for that, I actually thought maybe we could take a quick break from this and take a look at what these polynomials look like. And for that, of course, I'm going to go over to Mathematica, right? Because Mathematica has the ability to actually look at these wave functions. Okay, so we'll start here. Okay. So on the top line here, I've given psi over factor. I'm basically going to take the m omega and h bar, and I'm going to set it equal to 1. So all of my x's are going to be rescaled by the square root of that, and my wave function is going to be rescaled by that to the 1/4. And so I still want to keep around that 1 over pi to the 1/4, and that's just so that I can get these things to normalize correctly. Again, think about it as setting m omega over h bar to 1. The way that Mathematica does the Hermet polynomials is that it starts with the first argument in Hermet is the polynomial of order n, right? So n equals 0 is just the constant term, n equals 1 is the polynomial that goes as x, n equals 2 is the one that goes as x squared, but it also has an x and also has a constant, right? And so this is what order polynomial do you want, and then of course what variable, and so we're going to be using x. There's this other piece of the normalization, and then there's that Gaussian piece that we had to build the full wave function psi. And so I'm going to evaluate this just to store these, right? And now I can plot a couple of them. So here's the n equals 0. Here's the ground state. Here's the lowest possible energy, where it just looks like a Gaussian because the Hermet polynomial is just a constant. I can also look at the first excited state, right? Where, again, it looks Gaussian-y, right? It's damped off at the tails, but now I have a wiggle in it, right? And that's because the first Hermet polynomial goes as x. And then there's a second one, and there's a third one, right? And in fact, down here, I can generate a table that's just going to give me the first 5, right? So n has to start at 0 here. Here's the Gaussian, and then there's the first one, the second one, the third one, the fourth one, and it's awfully nice that Mathematica stores all of these. One thing to note here, right, and this goes back to our derivation, that if I have the fourth order Hermet polynomial, it only has 4, 2, and 0, right? Because alpha sub n plus 2 is related to alpha, right? And so I only have, they're either going to be even functions or odd functions. And I can plot them all together. I think it just looks pretty. You can see the Gaussian there. You can see the first one, the second one, and they wiggle away. Okay, and this is a good way of visualizing that. In fact, although the energies are something that was quick to write down, these wave functions are hard to write down, but they still sort of make sense to us when I plot them. And if you're worried about normalization, you can also check that the second state is normalized, the first state is normalized, the 41st state also normalized. Okay, it's going to take, they're integrated to 1. Okay? Okay, so was all of that math worth it? Well, probably. I mean, we got to learn some cool stuff about differential equations. We got to remind ourselves that in our hearts we're mathematicians somewhere. Was there an easier way? I mean, that final expression of h bar omega times n plus a half, it almost feels like it doesn't require. I mean, there must be an easier way to get to that, and that's something that we'll look at in the next video. Okay, but the take-home that we have is that we can do this problem the old-fashioned way. So if I have a quadratic potential, then I can solve for the eigenfunctions of that potential, and I can solve for the eigenvalues of the energies of that system, and I get this neat answer that the energy levels are separated by a constant. And why is that so important? Well, that's so important, right? Because because almost every potential has some sort of approximate minimum, and the energy levels in that approximate minimum are given by this expression. Okay? See you next time.